I'm Frank Sanders, Senior Technical Fellow at the Institute for Telecommunication Sciences, ITS, which is the Boulder, Colorado laboratory of the National Telecommunications and Information Administration. I'm a high-level subject matter and technical expert in electromagnetic compatibility between and among radio systems and even non-radio systems. Broadly speaking, NTIA is the spectrum management agency for the federal government. Everyone has heard of the FCC, which manages non-federal spectrum, and the FCC, the Federal Communication Commission, is a commission of Congress. All federal agencies, so for example, Department of Justice, Interior, Federal Aviation Administration, Department of Defense, etc., all executive branch agencies that answer to the White House are managed ultimately through the Interdepartment Radio Advisory Committee, the IRAC, which is chaired by NTIA. So our broad mission is to conduct spectrum management for the entire federal government. So we are a general purpose technical laboratory to support American telecommunication policies and operations for the federal government and specifically for the White House. Radio systems and technologies are a core part of all the work that we do. Ultimately, we are tasked with making radio systems operate with each other harmoniously across the entire radio spectrum. So the majority of the work, or the vast majority of the work that we do in Boulder, is devoted to compatibility and coexistence between and among federal government radio systems, but also, because those systems also happen to operate with a lot of non-federal systems, we also do end up working with non-federal systems as part of our spectrum mission. We work with pretty much every type of radio system you could imagine, including aeronautical mobile, marine mobile, land mobile, cellular, point-to-point microwave systems, space communication systems, but my personal favorite, and the one that really involves a lot of the work that we do, is radar systems. And these include radars for weather surveillance, radars for maritime operations, radars for air surveillance, for air traffic control, radars for defense systems, radars for environmental sensing, pretty much you name it. We work with frequency ranges all the way from extremely low frequency down at a few hertz, all the way up to 18 gigahertz on a regular basis, and sometimes as high as 40 gigahertz. The parts of the radio spectrum that are currently of the most interest to a lot of policymakers and to industry and to government agencies are between about 1 gigahertz to about 4 gigahertz, and even extending up as high now as more like even 6 to 8 gigahertz. So I'm going to say the middle portion of the microwave frequency range has become of great interest. We've worked with coexistence and compatibility between 5G systems and radar altimeters. These are the radars in airplanes that tell airplanes how high above the ground they are. So the 5G radar altimeter journey begins with a spectrum auction. The FCC made some spectrum available for 5G transmitters, which had not previously been available, and that spectrum was at and below frequencies at about 4,000 megahertz, 4 gigahertz. Now, radar altimeters operate between 4.2 to 4.4 gigahertz. There are two ways that radio interference could or might occur. The one way that everybody always thinks of, which can occur, is that the unwanted emissions from one set of transmitters, like 5G, that are not in the 5G band, but rather are up in the radar altimeter band could cause interference to radar altimeter receivers directly on the radar altimeter frequencies. The second way that interference can occur, the receiver is not well filtered on its front end, not filtered well enough so that it only sees what it's supposed to see, which is its tuned frequencies and a little bit of spectrum on either side. This is the window it's supposed to see in. What can happen instead is the receiver has a window in its front end that's this wide. It can be many gigahertz wide. And when that happens, the intentional licensed transmitter frequencies of a system like 5G, which are hundreds of megahertz away from the frequencies of the receivers, can cause the amplifiers in the receiver radio frequency front ends to overload. The overload occurs on the licensed, allowed transmitter frequencies of the base stations like 5G. When this happens, the receivers experience interference, but the only solution to that interference problem, if it occurs, is for the receivers to have better filtering on their front ends so that they only see narrow spectrum windows that are right on or about on the frequencies that they're trying to receive. And the FAA has issued some notices saying that they are working with altimeter manufacturers and airlines to get improved filtering installed on some radio altimeter receivers where indicated. This approach to solving technical problems by approaching them scientifically and quantitatively and coming up with either answers that say there's not a problem or answers that say there is a problem, but which have a technical solution, which is as follows, is an example of how we like to do our work and then communicate our work to the American public, to the American Congress, and to the White House, the U.S. administration, so that administrators, policymakers, etc., can make informed decisions about how they want to address these kinds of problems and get them resolved. Telecommunication research, development, design, implementation, deployment is really a lot of what the world is about now at a technical level. The world is about a lot of other things, maybe on a non-technical level, but at no time in human history has there ever been this kind of concerted, concentrated development on designing and building various types of communication systems. And the last mile or the last 100 miles of connections on these systems are typically radio links. A person who is an expert in radio system design, radio system engineering, radio system operations is not going to be lacking for job opportunities. Not only do we need people who have a broad technical grounding in science and math, and that is crucially important, absolutely. We also need people who have a broad grounding in the humanities, people who understand language and languages, and we need people who understand philosophy, and we need to be able to bring these kinds of diversity into every area, I think. And I know that radio spectrum engineering per se is just about, we'll say transistors, resistors, math, antennas, and etc. But ultimately, we need a really well-grounded, broad, diverse group of people working in probably every area, including radio technology. And in the world that we're living in, we need people who understand the big picture, the broad picture, and who see how the particular technical work that they might be doing in a particular time and place fits into that bigger, broader picture.